Hi everybody, in this video we are going to work on a BGP lab. We will learn the operation of these 12 BGP attributes, how BGP selects the best path, and how we can modify each attribute to force the selection of the best path over another path. Before starting, I want to take a brief look at the topology to better understand the dynamic of our lab. Our lab is very basic. We have a transit router, 2 road reflectors and 3 PEs that make up the IGP. We run OSPF for this IGP and iBGP between the road reflectors and the PEs. We have a VRF called BGP-lab in the 3 PEs. In this way we have an MPLS. Finally, we have 2 customer edge that run eBGP with the PEs. Router 1 has 2 WAN interface, one with PE1 and the other with PE2, and advertises the loopback 5.5.5.5 to the MPLS. Router 3 has a single one with PE3s and advertises the loopback 7.7.7.7. From this device, we will perform pin and trace tests to confirm which path is being taken to get from one loopback to another. We will modify the BGP attribute over MPLS to choose a different path, and from the router we will confirm that path. All the information regarding this lab, image of the router, configuration templates, topology and the rest, I share in the link that I leave in the description of this video. Okay, let's start with our lab. Our lab is already running in the if program. Here we are in the PE3 console. Let's check the status of the BGP routing for the loopback IP 5.5.5.5. We do it with the command show BGP VRF BGP-lab 5.5.5.5. With this command, we can see that we have 2 available paths to reach the loopback of router 1. This one that we received through iBGP with router reflector 1 and advertises by PE1. This is the IP address of PE1. Let's remember our topology. PE1 has IP address 10.1.1.1 and the second path through the iBGP with router reflector 2 and advertises by PE2. The IP of PE2 is 10.1.1.2. We can also see that the best path currently is PE1. Right here we see it is the best path. Okay, now go to the console of router 2 and we send a pin. Pin 5.5.5.5 source 7.7.7.7. Okay, we reach the loopback of router 1 by pin. Now we make a trace. Trace 5.5.5.5 source 7.7.7.7 numeric. In the trace, hop 4 confirm that we are reaching loopback 5.5.5.5 through the first one of router 1. This confirms the best BGP path we saw in P3. But well, what is the current reason for choosing the path through P1? We can see the reason repeating the command but adding this best-path-reason. Okay, the command would be like this: show BGP VRF BGP-lab 5.5.5.5 best-path-reason. Now the command output shows the following additional line: best path evaluation. And we see that the reason is that this path has a higher IP address than the other path chosen as the best. Okay, but which IP address are we talking about? The one of the router? No. In this case, they are the IP address with the BGP neighbors. That is 1.1.1.1 with router reflector 1 and 2.2.2.2 with router reflector 2. How can we prove this? Well, we are going to modify the neighborhood between P3 and router reflector 2 so that row reflector 2 has a neighbor IP address lower than the IP address of row reflector 1. First, let's verify the configuration of router 2. We give a showroom. We have loopback 0, currently the one that established BGP with P3, and a loopback 1 with IP 1.1.1.0. From P3 we have ping with this loopback. Now go to the BGP of P3, make a showroom by section router BGP, and okay. We shut down neighbor 2.2.2.2 and wake up the neighbor 1.1.1.0. Now BGP for 1.1.1.0 wake up. We validate loopback 5.5.5.5 again, and we see that now the BGP session with router reflector 2 is with IP 1.1.1.0. We also see that now P3 selects P2 as the best path through router reflector 2, and the other path through P1 reports a higher IP address. If we do the ping and trace again from router 2, we see that now latency is higher, and in the trace, hop 4 takes the path through the second one of router 1. Well, we have forced attribute 12, and it is true that it prefers the path through the lowest IP address. But why were none of the highest priority attributes from 1 to 11 taken into account? To know this answer, let's verify one by one what values each path has for each attribute from 1 to 11. Let's first look at attribute number 1, wait. This is the attribute with the highest priority. If two or more paths know how to reach the same destination, the wait is the first attribute to break the equality. The higher the wait, the higher the priority. The path with the greatest wait will be the best. But if the wait is the same for all paths, then the next attribute is evaluated in order of priority. In this case, the local preference is continued, and so on until one of the attributes break the equality. So, to see the weight between the two paths in our lab, we do it with this command: show BGP vref BGP-lab. Okay, for network 5.5.5.5, we have two hops. One through P1, this one, and this other one through P2. If we go to the wait column, we see that both have 0 wait units. This is the default wait that is assigned to a network in BGP. Since both paths have the same weight, the BGP begins to evaluate the following attributes. We then move on to evaluate the local preference. Again, like the previous attribute, the path with the most units is the best. That is, the highest local preference will have the highest priority. Well, we can validate the local preference with this command: show BGP vref BGP-lab. We can see here that both paths have a local preference of 100 units. We can also see this attribute with this other command: show BGP vref BGP-lab 5.5.5.5. Here we can also see that each path has the same local preference. Since we have the same local preference for both paths, we move on to evaluate the following attributes. Okay, now origin. BGP prefers the path that the local router originates. In the BGP table, you will see next hop 0.0.0.0. Currently, in our lab, the paths are originated by P1 and P2. Therefore, this attribute does not apply at design in our lab. So we go on to evaluate the following attributes. Okay, now shortest aspath length. With the same command, show BGP VRF BGP -lab, we see that both paths have the same aspath, a single AS in the path. Let's go with the next attributes. Now, lowest origin type. We have three types of origin in the following order of priority: IGP, EGP, and incomplete. We can validate this with the same two commands that we have been using. We have the origin code I. It means IGP for both paths. With the other command we have the same, both paths with IGP origin. Okay, then we move to the next attribute. Now, lowest met. BGP prefer the path with the lowest metric. Again, we can validate it with any of the two commands. Fine, we can see that the metric for both paths is 0, here and here. Up to this point, the first 6 attributes register the same value for each path. So, go to the next attribute. eBGP path over iBGP path. In our lab, the network 5.5.5.5 is learned as an internal route for both paths. We can see it here and here. It is internal because peers and row reflectors use the same local autonomous system. Therefore, BGP between routers with the same AS establish iBGP session. So, next attributes. Okay, now lowest IGP metric. Here we can see that both paths have an IGP metric of 12 units. This metric is from OSPF. Okay, next attributes. Now, oldest path. The time the network was updated is verified. Our lab have the same date and time for both paths. So, let's go to the next attribute. Lowest router ID source. We can see it in this file, originator. Both are originated by the same router ID 10.1.1.1. Then, next attribute. Minimum cluster list length. We can see it in the following file. Cluster list. The list for each path contains a single device. For this path, row reflector 1, and for the other path, row reflector 2. Therefore, the size of the cluster list is 1 for each path. So, we have gone through the attribute by priority from 1 to 11, and so far, none of them managed to break the equality between paths. Then we come to the last attribute, which was our first test, attribute number 12. Prefer the path with the lowest IP address. Given that in BGP on the same global routing table or RVRF, a BGP session cannot be established with the same address more than once, and if all the other higher priority attributes do not break equality, this last attribute does. Since a BGP neighbor IP address on a router can never be equal as another. Well, now that we know the reason why our lab breaks equality with the last attribute, and we have proven that by modifying the neighborhood with a lower IP address, the best path is changed. Now we are going to go up attribute by attribute to force one by one from lower priority to higher priority. We are going to test attribute by attribute. We will verify the preference path and modify the attribute to force the change of the best path, as we did with attribute number 12. Okay, let's go with attribute 11, minimum cluster length. To validate this attribute, we have to create a cluster with a length 2 row reflectors. That means we have to add one more row reflector to our lab. Currently, our lab is in the initial state. The best path is row reflector 1 through P1. We validate it with a trace from router 2. Okay, the best path is P1. Now, on IFNG, I already have the tier reflector active. What I am going to do is simple. On P3, shoot this BGP session with row reflector 1 and not shoot the session with row reflector 3. And this is what our topology looks like now after the change. Well, now we have that the path between P3 and P1 has a set of row reflectors that make up a cluster. Let's see what the 5.5.5.5 network over BGP looks now in P3. We execute the command show BGP feedered BGP-lab 5.5.5.5 best-path-reason. What we can see is that the path with row reflector 3 has a cluster list with 2 row reflectors, row reflector 3 and row reflector 1. Right here we can confirm it. And the theory says that BGP prefers a minimum cluster list length. We can confirm that because now the best path is P2. That path will only have a single row reflector, and the other path a cluster with 2. Let's validate our pin and trace from router 2. Fine. Hop 4 confirms that we reach the network via P21. In this way, we have modified attribute number 11 and it works. Now let's go with attribute number 10. Lowest router ID source. Right now, both paths come with the same router ID, 10.1.1.1. Since currently the best path is preferred through P2, so we are going to modify the router ID of P1 to forward the path through this P. We go to P1. This is the BGP configuration, and we confirm the current router ID 10.1.1.1. We change it to 10.1.1.0, which is lower than the current one. We made a commit and we have it ready. We wait a few seconds for the BGP to update. Well, after a few seconds, we return to P3 and check again. We can see that now the path through P1 has the BGP router ID 10.1.1.0, and regardless of the fact that it has a cluster list with 2 row reflectors, one more reflector than the other path, it discards the cluster list attribute and prefers the path through P1, as it has a BGP router ID lowest. Okay, we confirm with the trace from router 2 and we see the path through P1. This way we check attribute 10 works. Now let's go with attribute 9. To test attribute 9 oldest path, we will validate it with the loopback 7.7.7.7 of router 2, and we will add a third router that will announce this same loopback. We do this because the oldest path attribute only applies to external routers. Remember that the ones we have with the row reflector are internal, as they have the same AS. but the ones we raise against the customer routers are external, as they have a different AS. Okay, we already have the router 3 active with its respective BGP app and advertises the same loopback as router 2. Router 2 has the BGP router ID 7.7.7.7 and router 3 the BGP router ID 8.8.8.8 and in the PE with our usual command. Right now we can see that it does not matter that one has a lower BGP router ID than the other. What counts now is the oldest path. At this moment, the oldest path is the one with router 3. We can see the date and time here, and the other path is younger. We see it here. Therefore, P3 takes router 3 as the best path. We also verify it by making a trace, but now from router 1 to loopback 7.7.7.7. We confirm we reach it through router 3. Now we are going to the loopback on router 3. We wait 1 minute and reactivate it. What is expected is that in P3 the best path will change to router 2 because this will become the oldest path. Then shut down the loopback on router 3. In P3 we see that the loopback is only known through the path of router 2. We wait 1 minute. After a minute we reactivate the loopback and go back to P3 to see what it looks like. Okay, we can see that in fact now the path through router 2 is the oldest and the other report that is younger. We make a trace again and see that it is reached through router 2. In this way we confirm the operation of attribute 9 oldest path. The next attribute, lowest IGP metric path. Currently we have the same IGP metric for both paths. We can see it here and here. Those metric of 12 units are assigned by default to our OSPF, which is the IGP of our lab. So, to change the path, we simply go to the OSPF of P1 and add more metrics. Well, this is our P1. We validate the current OSPF configuration with the show run of PF command. This is the configuration. We did it and add an additional cost of 20 units. Save change and wait a few seconds to validate again in P3. We check again in P3 and now we have that the IGP metric for the path through P1 changed from 12 to 31. This makes the path through P2 now the best. We confirm with trace from router 2 and we have that it is reached by P2. Attribute 7. eBGP path over iBGP path. Given that the two paths through router vector 1 and router vector 2 are iBGP, we need to add one more path that is eBGP. So again, we add the tier router and from this we announce loopback 5.5.5.5. This router 3, let's remember, it has this AS. And establish eBGP with P3 because they have a different AS. Okay, we already have the eBGP app with router 3. We validate again what the 5.5.5.5 network looks like on P3. We see that now there are 3 paths to reach the 5.5.5.5 loopback. The path through P1 and P2 are internal, iBGP, and the path through router 3 is external, eBGP. Therefore, the path through eBGP is preferred. We validate it with the trace from router 2, confirm it is reached by router 3. Okay, before continuing, we turn off router 3. Now, the lowest metric. Let's remember that currently the path through P1 and P2 have metric 0. At this moment, the path through P2 is preferred, so we are going to modify the metric of this path to make it greater than the metric of P1. We can do this from router 1 because the metric is an exportable attribute. Then we go to router 1, we create a roadmap and add metric 1000 to it. Now we apply it to BGP neighbor of P2 on the way out, just like this. Finally, we do a soft clear on output for the BGP neighbor with P2, and that's it. We validate again in P3. We can see that the metric for the path through P2 changed from 0 to 1000, and now the best path is P1. We confirm it with the trace and it is okay. It is reached through P1. Ready attribute number 6. The lowest metric is the best path. The next attribute is lowest origin type. For this attribute, we have these 3 types of origin: IGP, EGP, and incomplete. Currently, for both paths, there is the same type of origin, IGP. We are going to force the path through P1 by changing the origin to incomplete. We can do this from the router 1 because this parameter is also exportable like the metric. We do it with a roadmap. We give it any name and we configure set origin incomplete. And we add it in output mode to BGP neighbor that we have with P1. We execute a soft clear on egress for the BGP neighbor. In this way, we update the new attribute information on BGP. We now go to P3 and validate again. We can see that the origin for the path through P1 is no longer IGP and is now an incomplete origin. We also see that the other path that is still IGP origin is now the best path. We validate it with the trace and hop for confirm that it is reached by P2. We have checked attribute number 5. Now let's go with attribute number 4. Shortest AS path length. Let's first check the current status of the AS path for each path. We can do it with either of these 2 commands: show BGP vrf bgp-lab or show BGP vrf bgp-lab 5.5.5.5.5. The first command shows us the AS path in the column called path right here. We see that the AS path for each path has unique AS 65,200. This same can be validated with the other command here and here. Well, then we are going to manipulate the AS path for the path through P2 so that it has a longer AS path than the path through P1. We do this again on router 1 with a roadmap because the AS path is also an exportable attribute. Okay, what we are going to do with the roadmap is apply a technique called AS path prepending that allows several AS to be added multiple times within the same path. Let us remember that currently router 1 already has a roadmap applied on the output for the BGP neighbor P2. We can see it here. It is the one we use to modify the metric, so we can add the AS path prepending to it or create a new one. This is how everyone prefers it. What I am going to do is create a new one with a generic name, and I will keep the metric we had and add the AS path prepending, just like that. Roadmap BGP-path set metric 1000 and this other line set AS path prepend and the times we want to add an AS. For the example, I add the same local AS of the router 3 times. 1, 2, and 3. This is how the roadmap looks. Now, on the BGP neighbor in output, we rewrite with the new roadmap. We do a soft clear and that's it. We go to P3 and validate how it looks. We repeat boot commands and now we see that the AS path for the path through P2 has 4 AS. The first is the router's own local AS, and the other 3 are the ones we have added with the prepending technique. We also see that the effect it causes is the expected one. This path has a longer AS path, therefore now the best path is P1. We ratified it with the trace. Hot force confirmed is reached by P1. In this way, we finish with attribute number 4. Let's go with 3. Prefer locally origin. This attribute indicates that it prefers any network that is configured locally on the router over the ones known by a BGP neighbor. For example, if in P3 we configure loopback 5.5.5.5 on a WAN interface or on a loopback and put it within the local BGP, the router will prefer this IP that is directly connected to the router than any other through BGP. Let's do it. I configure a loopback and I include it within the BGP lab VRF. I put the loopback IP 5.5.5.5 with its respective max, and we add it to the VRF added family. Router BGP 14090, added family IPv4, VRF, BGP lab, network 5.5.5.5 and mask. Okay, we already have the loopback in P3 has a directly connected interface and it is part of the BGP for the VRF. Let's check now how it looks. As we can see, we have that the next hop for the 5.5.5.5 network is 0.0.0.0. This indicates that it knows it locally because the next hop is itself. If we do a pin and tray test, we see that it is reached, but of course, who responds is P3 itself. Okay, this type of configuration really does not make much sense to do it in an MPLS or in a router, unless you want to do some troubleshooting to test device by device along a path. Okay, once attribute 3 has been tested, I'm going to shut down the local loopback in P3 to continue with the 2 attributes that remain. Let's go now with high-host local preference. This attribute is local and is not exportable. By default, BGP registers every network that learns from a neighbor with local preference 100. We can see it here in this column, and here with any of the two commands that we have been using. Okay, since at this moment P1 has the best path, we can force the other path by manipulating the local preference in two ways. The first one, making the local preference for the path through P1 below 100, that is 99 or less, or increasing the local path preference for P2 with a value greater than 100, that is 101 or more. Both option works. What matters is that the path you want is the best, has a greater local preference. So let's try the second option. As we say, this attribute is local. Therefore, we are going to manipulate it on P3. The first thing is to create a row map that executes the action of assigning a local preference greater than 100. For example, 200. Just like that. Row map local pref set local preference 200. Okay, we already have our row map. Now, since we want to modify this attribute for the path through PE2, then we are going to apply into the BGP neighbor again roller vector 2, which is the path with PE2. But in which direction? In or out? In this case, it must be input, because we modify what we learn, not what is advertised. So we do it like this. Okay, now make a soft clear inbound or wait a minute or two for the BGP table to update. For the example, I make a clear to no wait. Okay, let's validate again. Cool. We see that the best path is P2 because it has a local preference of 200 and the other path has a lower local preference. We repeat our test from router 2 and confirm. Hold for throw P2. Nice. This way we get to the last attribute. Highest weight. Like local preference, weight is a local attribute. By default, BGP assigns a weight of 0 unit to everything it receives over BGP. We can see it here in the weight column. Currently, the best path is through P2. So, as the attribute indicates, we aren't going to give greater weight to the path through P1. We also do it with a row map as follows. Row map weight 2000, set weight 2000. Now we apply this row map to the BGP neighbor of router vector 3 who has the path to P1. We apply it in the incoming direction. We do a soft clear for the BGP router vector neighbor, and that's it. We now have E1 as the best path because now we have a weight of 2000 and the other path has a lower weight. And that's all for this lab. If you liked this video, give me a like and subscribe. Thank you. See you later in another video.